So let's continue to explore our data, and we're doing some exploratory data analysis, or EDA. So we've collected some data through a survey, we have maybe a database of information. Now we're diving into what the data can tell us. In our previous videos, we looked at descriptive statistics. In these next coming videos, we'll look at inferential statistics. For each of these, because you've probably already taken a stats course or modules in statistics, then you already know the basics. So what we're looking at here is what's the appropriate procedure for the type of data that we have. It's important that we know our measurement scales. And then we need to know what is it that this is telling us. And then, of course, how do we do it in Python as we're ramping up our machine learning and data analytics. All right, so we did descriptive statistics. We summarized the data set of a subset of the population. Now what we want to do is inferential statistics, which means we want to draw conclusions about the greater population. So can we take what we got from the survey or from our database and extrapolate to the rest of the group, the bigger population that it represents? All right, so we're looking at our survey. Remember our bargaining survey. We surveyed a number of union members about what their priorities are for bargaining. So we're going to look at that data set. And then we're also going to be using our customer relationship management database that we've looked at in some previous videos. So here we have data that's tracking our salespeople, contacting potential companies about, here we're building websites for these companies. So we're looking at data related to the company itself, what type of company they are, how much money do they make, how much is the contract potentially worth to build them this website. And then we have information about the contacts that we have, the communications that we have. So the amount of time we talk to them, the talking speed, the listening ratio, the average pauses, how well this relationship is building as we try to move from a qualified, so we've identified them as a potential customer, to contacted, we've reached out, to showing them a demo, to providing them a proposal, to negotiating the contract, and hopefully winning them as a client. So we're going to be moving through these data sets as we do our inferential statistics. And so we are working in this inferential statistics Python notebook. You can find this notebook at drstephpowers.github.io/BIA. We are here in chapter 5 of the Business Intelligence and Analytics Handbook, and we are doing inferential stats. Once you are here, click to open in Collab. And then, of course, you need to log into your Google Drive and save a copy so that you can amend and run the code. You'll notice here that we're going to be using data sets. We're going to use our bargain numeric. This is the coded data set for the survey. And we're going to use a data set related to the customer relationship management database. So we pull that data out and we have what we call CRM clean. So make sure you put that database, that Excel spreadsheet, into your Google Drive. And then you're going to need to link to that location so we can pull that data. And that's because we practice different inferential statistics. The survey covers some types of data, but not all. So we need a second data set to showcase the different types of inferential statistics. All right, so let's go in. When we are doing inferential statistics, we're going to need our pandas package, and that's because we are dealing with tables, data frames, and we're pulling data in from Excel, so we're using pandas for that. So that's called import pandas as PD, so we can use that later here. That's this PD. And then we're using stats packages from Skippy, so skippy.stats, and just for ease, we'll call that stats. So always start with your basic packages that you need to get started. And then because we're pulling in Excel files that you've saved to your Google Drive, mount them. I keep forgetting to replace this here. I've changed it so that instead of just calling it from the Google Drive, you've learned to pull it from your own, and that way you can keep your data and don't have to have it somewhere else. So here we go. From Google.collab, import drive, mount the drive. So we do that to make sure that it is connected to our own Google Drive. And this is not giving access to anybody else to your Google Drive. This is your Python notebook linking to your Google Drive for your data. And it's simply all for you to have your own access. Okay, let's make sure that runs. Once that does mount, then we need to import our data. These are Excel files, so they read underscore Excel. If they were CSV files, it would be read underscore CSV. The extension here on these Excel files is XLSX, and we are going to, this part, everyone is true for everybody, and then it's the name of the folder that you have it in. I have it in BIBA handbook, and then I have a folder inside that that's called chapter 4, and then the file itself is bargain numeric. For the CRM database, as we're pulling in, we are going to call it DF3, and that's because DF1, the original, was the cleaned bargaining database. DF2 here is our coded bargaining, so we'll call that DF2. You can call it whatever you want. And so DF3, I mean, if you want to make it cleaner and call one CRM equals and one bargain numeric equals, you don't have to use DF1, DF2, DF3. You can make it something that helps you remember what it is. The DF3 one here is our CRM clean data. Notice that this import has a comma sheet underscore name equals sheet 1. And that's because if your Excel file has more than one sheet, you know, those tabs at the bottom of Excel, you need to specify which of those tabs, which of those sheets has your data in it. This CRM database, we've created these drop-down menus to populate the database so that as we're filling out the information for the organization, we would simply choose from a set list. And so there's actually a second sheet in there that has the lists that create those drop-down menus. And so we only want to pull the data from sheet 1. So that's why this extra piece here. And later when we pull in Excel files that have data sets in every tab, we want to specify which data set from which tab is the one we're actually analyzing. Now, a bunch of these tests you learned about in stats, and so we don't need to dive into details about the different statistical tests. What is most important here is which one do you use when and what does it tell you? So it's really important for your data, whether it is your survey or whether it is your database, to create that data dictionary where we have specified what is the measurement scale for each field or variable. And that's because this document right here, which you can find in my book, is kind of this Bible that you need to hang on to. And it's what it does is it tells you which test, depending on what you want to know and what type of measurement scale you have. So we're going to go through each of these. The black squares are the different tests. And so we can actually take all these different statistical tests and we can group them together, whether we are looking at a single question in our survey or whether we're comparing the answers from multiple questions in our survey. That's the part here on the right. And whether we are looking at one group or whether we are comparing two groups. And if we're comparing, maybe we're comparing more than two groups. These are going to be different tests. When you're doing two groups or more than two groups, we have to look at, are we looking at information that is different people in the groups or the same people in the groups? Okay, that's going to lead to different ones. And so we're going to be moving through over the next couple of videos these different inferential statistics, and we're going to group them then by the questions they answer and the measurement scales that we have. So we're going to be diving into that. And so let's actually just start here. So let's look at comparing to a value. So let's start here on the left side. And I'm just going to zoom in a bit more so we can read it clearly. Now, if we're simply describing, we would use our proportions, our median, our interquartile range, our mean, our standard deviation. And our previous videos showed us how to do this in Python. So you already got that section covered. That's your descriptive statistics. Now let's get into our statistics. All right, so let's say we want to compare to a value. So if we have nominal data categories and we want to compare that to a number, we use a chi-squared goodness of fit test. If we have ordinal data and we want to compare to a number, we use what's called the Wilcoxon One Sample test. If we want to compare to a value and we have ratio or interval data, we need to ask ourselves whether we know what the distribution is. If we think it's likely there's a normal distribution because there's some kind of measure of central tendency, a mean, most of the data congregates around and then is distributed less and less the farther you are away, then we use a one sample t-test. If we don't know the distribution, so perhaps we think there's an equal likelihood of different responses, so more uniform, so it's not normal or we don't know, then you go down the measurement scale. Remember we talked in our previous video about how you can go down, you just can't go up. Then we go down and we use a Wilcoxon One Sample test. So let's take a look at how that works. All right, so we're comparing to a value and the chi-squared goodness of fit test is going to see here, is there a difference in categories? So let's go to question 23 of our survey. Question 23, what campus are you associated with? So what we look at with this test is we are looking at those values in question 23, and we're looking for, is there a difference? Is there a difference in the number in north, south, east? That's what your chi-squared goodness of fit test is going to tell you. Now, when we do any type of inferential statistics, we need to run the test and get a p-value. So let's talk quickly about what a p-value is. When we look at a test, we have error. And so the question becomes, how much error are we willing to have? And in stats, as you recall, a type 1 error is alpha. This is the chance that we say that there is a difference, and in this case that there's a difference in the amount of people at the east, south, and north locations, when in reality there's no difference. So we test it, we think we found a difference, but in reality there was no difference. That's alpha. And often you'll have an alpha of say 0.05. If you have a smaller sample size, you might go with a 0.1, a 10% chance that you're wrong. And if you have a large data set, you're doing medical studies, you might have an alpha that's maybe 0.01 or 0.001. Okay, so it really is going to depend on how much you're willing to be wrong, saying there's a difference when there really is not one. Now I'm just going to move my head here. Oops. Okay, let's move the slide. Let's try moving my head instead. Here we go, head. And when we look at the other type of error, type 2 error called beta, this is the probability that you detect no difference when there truly is a difference. And so there's a trade-off between this alpha error, type 1 error, and beta, type 2 error. So if you are trying to minimize one, the challenge is that the other one goes up, and that's what this chart here is showing you. That if we move this line that divides, where's my line? If we move this line that divides between what we're testing, then the problem is that if you're trying to minimize type 2 error, you're going to increase type 1 error. And if you're trying to minimize type 1 error, you're going to increase type 2 error. So there's this trade-off between. So we select an alpha, how much we are willing to be wrong. So if we are willing to accept a 5% error, an alpha of 0.05, okay, then what we're going to do is run our test, and our test is going to take our sample try to extrapolate to the greater population, recognizing that there's a probability associated with that, taking that small sample to the bigger group. And so depending on how much variability there is in our sample, how united that data is will determine how strong that test is. And we compare that p-value to our alpha. And so what we want to do is we want to look at p-value. If I go back into our tests here, go back to our inferential statistic. When you run it, you get a p-value. You are looking for a p-value that is smaller than your alpha. Okay, so if we have an alpha of 0.05 and we run this particular test and we get a p-value of 0.72, this means that we are not detecting a difference. Okay, so our alpha, go back, remember alpha was detecting a difference when there was no difference. So if you have a p-value that's less than your alpha, then you can be confident that there is a difference, that you reject that null hypothesis, because that results of your data analysis of just your sample is so strong that the probability of the difference is less than your risk that you say there's a difference when there's no difference. If your p-value is larger than your alpha, then the concern is that there could be no difference there, you can't detect it, and so then we go with the null hypothesis, or we just can't confirm the alternative. So let's go here. Chi-squared goodness of fit. Is there a difference in categories? We use skippy.stats. We import the command chi-squared. It's a chi-squared goodness of fit. We are going to take our data frame 2, that's the coded bargaining data, do the value counts for question 23. That's when we want to see, is there a difference between north, south, east? And then what we're going to do is we're going to do a chi-squared test on those value counts. So we import the necessary package to do this type of test. We create those value counts, those frequencies. We talked about that in a previous video. And then to do a chi-squared goodness of fit test, the command is chi-squared. We get a test statistic. What we want to focus on here is this p-value. Our p-value of 0.716 tells us that we do not detect a difference. So if the p-value is less than alpha, there's a difference. If the p-value is more than alpha, no difference. We can't detect it. Now, it could be that there's no difference, or it could be that our sample isn't big enough to represent the variability in the population. Okay, so chi-squared goodness of fit test is used when we have nominal data we're comparing to a value. And in this case, we're comparing to equal distribution between the responses in the question. So north, south, east, west, is it the same number in each? So it's looking at, is it a third, a third, a third? And in this case, it's pretty close to a third, a third, a third. We can actually see that here. DF2 obs. Okay. You can see that's pretty close to, numbers are pretty close to each other, and so we don't detect a difference in the number of people who responded north, south, east, west. Okay. So the test we just did looked at, is there a difference in the categories, assuming equal distribution was what we were comparing it to. But you don't have to use this test to compare to an equal distribution. As we noted previously, it is compared to a value. So you can actually specify what percentage should be each group, as opposed to just assuming that it's equal. So this next test that we have right here is to compare to percentages that we assume are not equal. So for example, we could actually specify that maybe half of the expected respondents are supposed to come from the south location, because maybe it's just bigger. And then we expect that there's going to be, the other half is going to be coming from north and east. So 25% from north, 50% from south, 25% from east. So we can do a comparison to whether or not the responses from the survey are equal to what we know in terms of our union members at the 3 locations, to see if we really got representation in the survey from the different locations. So you'll notice the first couple pieces are the same. We import numpy as NP. We do that here because we're going to create an array to compare it to. And then we use our skippy.stats to import chi-squared so that we can run our test. We do the value count. So we take question 23 and we have it look at how many north, how many south, how many east. That's the same as before. The additional code is this section right here. So the first part of the code says, okay, question 23 in the df2 table, that's our coded table, and it asks for the length of that variable. So what it's looking for is how many people responded to question 23. Because if we're going to say that we expect 50% response from the south location, 25% from the north location, 25% from the east location, we need to convert that into how many people do we expect that to be. Well, if there were 63 responses to our survey, then half of 63 should come from the south, 25% of 63 should come from the north, and so on. So that's what these two lines of code are. First, it's figuring out the length of that variable, so how many people responded to question 23, and then it is going to create an array using numpy. And that array consists of the breakdown we're expecting, 25, 50, 25, and it's multiplying it times the total number of responses to essentially get, as well, actually, let's just output it here. Let's go code. First, you can see df2 tot is the 63 responses to the survey. And then you can see here df2 exp is what we expect. And we're expecting, 0.25 of 63 is 15.75, 31.5 is 50% of 63, and so on. So these are the expected values, so that when we do our test, remember we're comparing to a value, we're going to use our chi-squared test to compare to set values. So to do that, we do chi-squared, and unlike before where you just had one piece of information you put into chi-squared, we then have a second piece here where we are going to set the expected values. So when we run this one, what we see is that we get our value, our test statistic here, and then our p-value. And notice that the p-value here is 0.038. If we have an alpha of 0.05, so we're willing to be wrong 5% of the time, based on the data here, what we can see is that there is a difference in the number here. So when we're looking at our test, we're comparing to the percentages that are not equal. And so we are rejecting this hypothesis here that this is the breakdown. Okay, so whenever we're doing a test, let's go back. What we're looking at our test is we reject the null hypothesis if there is a difference, and we fail to reject if there is no difference. And so in this case, what the null hypothesis is, the null hypothesis is this 25%, 50%, 25%. And according to our p-value of 0.04, then we did not get that breakdown. And of course, we could see that here because we don't see that breakdown. You would have to have a lot more in 2 than 3 and 1, and 3 and 1 be about the same for us to go with that null hypothesis and to have that p-value that's higher than the 0.05. So it's less than 0.05, and we reject the proposal that it is 25, 50, 25. There is a difference than the values we're proposing. All right, so we did nominal, we did ordinal. The last one, if we're comparing to a value, is a one sample t-test. To do a one sample t-test, where did it go? Compared, goodness. Oh, sorry, jumping ahead. We're not there yet. We didn't do our Wilcoxon One Sample test. So compared to a value that's ordinal, a Wilcoxon One Sample t-test. Just too excited, I guess, to get further on. This Wilcoxon One Sample t-test is going to use the command Wilcoxon from skippy.stats. And here we are comparing our value. Let's look at question 18. So question 18, do you agree with the following statement? My workplace is safe. Notice it's Likert scale. So this is ordinal data. And what we're looking at when we do a Wilcoxon One Sample test is we're essentially looking at the median compared to an expected value. So what do we think the median response will be to the workplace is safe? Okay. All right, so what we're going to do is we're going to say, okay, well, let's see if it's 4. So what you see here in the second section after we load in our packages is we want to take the length of question 18. So we looked at that previously, right? So what we want to do is essentially say, okay, how many responses were there to question 18? That's what this is. And then what we're going to do is we're going to repeat. So we're going to use NumPy to create a list where we just repeat over and over again what we expect the median to be. So if we're expecting people to say that they agree that their workplace is safe, 1, 2, 3, 4, agree, then what we can do is create this list where it just repeats 4 over and over and over again for the length of question 18. So we've lined it out here in 2 steps. You could just make it 1 by putting the length here, right? So instead of running this like this, we could instead just put this here, right? So we could run that instead. Okay, so you can run it as different lines of code until you're comfortable. You can start condensing it down as you get more familiar. But what we've done here, and I'll just show you what the output looks like. Of course, you can do that on yours too. Is we just have a lot of 4s for all the responses to question 18. Now, to do the Wilcoxon test, we do Wilcoxon, and then we are doing it on question 18 from our coded data. And then we want to do what is the median we expect to see. We expect to see 4. Okay, so that's what this is here, and we run this. Notice that we get a p-value of 4.955 e. That means we're using engineering notation, negative 0.07. So what that means is that there's essentially 6 zeros, so 0 dot, and then a bunch of zeros, and then 4.955. So this means this p-value is super tiny. Okay, so what that means is that when we look at this information, we're very strongly rejecting this null hypothesis. We're very much saying it is not 4. So it is not 4 in terms of how people feel about, what was the question? Workplace is safe. If you want to dig deeper, because of course we're exploring, we can actually graph this data to see, okay, this is telling us it's really not 4. So let's then plot it. Let's import matplotlib.pyplot. Okay, we're going to call that PLT to make life simpler. This allows you to do your graphing. And then I have NP here. We already imported NumPy as NP. You don't have to technically do it again. But it's always just a good habit to make sure the packages you need are there. And we can see here what we're going to be doing is we're going to be using NumPy to help arrange information. And so that's why I'm calling it again here. So just so we don't forget whether or not we did it previously. All right, I'm going to create a box plot. A box plot helps us see our max, our min, our interquartile range, our median, our Q1 and Q3. So we're going to do a box plot for the coded table question 18. Our x-axis, we're going to have it say safety. I'll just show you here. Okay. So we're going to have it say safety. I'm going to take this away and you can see the change here. So if I don't specify anything there, then what it gives me is it gives me this label 1. I don't want that label 1. So what I'm going to do is replace 1 with the word safety. Okay. And then my y-axis, if I remove this, Then you see this y-axis has 1.5, 2.5, 3.5. Well, it's a Likert scale. You can't have 1.5. It's just 1 or 2 or 3 or 4 or 5. So I'm actually going to add in this little piece here where I'm going to say create a range. That's what this is. I'm going to use NumPy to create a range that goes from 0 up to but not including 6. And I'm going to specify the step is 1 because I don't want these halves. I want whole numbers from 0 to 6. Okay? And then we plot it to show it. So here we go, from 0 up to but not including 6. We've labeled it safety. Here we have our box plot. The orange right there is your median. Our test was that we thought the median was 4. The median is not, it is 3. And we have one outlier. That's what you see, this little dot here means it's inconsistent with everything else. And so we had one person who felt really not safe, right? So in our score here, it says strongly disagree is 1. So we had at least one here that strongly disagreed about safety in the workplace. We can see some people strongly agree. We can see here what we're seeing here is that our box and whisker plot, it really should have this middle line, and then it should have an upper line of the box and a lower line of the box. We don't see a lower line of the box because Q1, the 25%, and Q2, the 50%, are equal. So 25% of the group rated safety as a 3 out of 5, and 50% rated it as a 3 out of 5. Okay, so that's what this box plot is showing you, and it shows you then the range here of responses. But here the point of this is, and we'll get into box plots more later, is that the median is actually around 3. So it makes sense that our test to see if the median was 4 rejected that. Okay. All right, so comparing to a value, ratio, and interval. If we know that we have a normal distribution, we do a one sample test. If we don't know about the distribution, maybe we think it's uniform, everyone has equal likelihood, then we would go back to the Wilcoxon. Because again, you can go down in your measurement scale, but you can't go up. So if we assume there's a central tendency and that as you get further and further away from that average, less and less people are in those categories, then we have a normal distribution. To do a normal distribution, so to do a one sample t-test, let's take question 24, which was the number of years that someone was there. So we're going to use from skippy.stats, import t-test one sample. That's what we're using here. Okay. And when we do this, it is unhappy when there are NAs in the response, when people don't put in a response. And so it gives us an error. So we have to add this piece here that we're going to drop the NAs from question 24 before we run the test. Then the other parts of your one sample t-test are, what are you comparing it to? So what if we think the average number of years that people are at the organization is 5? So pop mean equals 5. That's what we're comparing. That's the value we're comparing it to when we compare to a value here. The other thing you have to decide is whether this is a left-tailed test, a right-tailed test, or whether we are testing both directions. So the alternative is that we think that it's less. So we want to know, is the average number of years that people are here 5? And in comparison, we want to do less. So if we end up with a p-value that's less than 0.05, then that means there are less than 5 people or 5 years at our organization. Okay, so let's run that first here. Oh, got an error. Why? Because I didn't import the package. I have to import our t-test one sample. Now I can run it. I get a p-value of 0.99, which is telling us that they can't reject the hypothesis that the average equals 5. And that's because our test only looked at whether or not it was likely to be less than 5. So the fact that our alternative was less made us not reject the null hypothesis. Okay, so we can't go with the less than 5. We can go greater here. So maybe that we want to test the average 5 versus an alternative where the average is actually more than 5. If you went that direction instead, you'll notice your p-value is 3.74. Our engineering notation with a negative 0.05, that means there's a bunch of zeros in front of that 3, 0.000, and we get a very small p-value. So then it's much more likely that the average is greater than 5. And so if we wanted to see this in the data, we could see, for example, that for question 24, there's a lot of variability, right? Standard deviation we found before was 8.4. We could plot the variability. So there's a package called Seaborn and a data visualization called Swarm Plot. This swarm plot lets you see, here's our swarm of bees, and plots it out. So with swarm plot, you need to define what's your data. So this is df2 and which variable, 24, and then it plots it. So what we can see here, it's unhappy because somehow my parentheses disappeared. All right, so here what we can see is, you can see there is a swarm. There's a bunch of people with less than 5 years at the organization, but you can also see there's all these people with more than 5 years. And so while there is this congregation here, it is outweighed by all these extra years. So if we were to look at, for example, more the mode, right, we'd be down here, but because the average gets skewed by extremes, the actual average is going to be more than 5 for our sample, and it's likely that it's more than 5 for the greater number of members in our union.